Hello, everyone. Thank you for coming to my presentation. My name is Jason Hughes. I'm a first-year grad student at Fordham University studying data science. This is a paper that I did with my advisor on fairness in optimal transport. So the title of our paper is Fair and Distributed Dynamic Optimal Transport for Resource Allocation over Networks. So our motivation for this project was to create an allocation scheme that was fair, because in the traditional optimal transport paradigm, resource allocation can be unfair. For example, you have the classic mines and factories example for optimal transport. If a mine provide all of its resources to one factory, that might be optimal, but it will drive other factories out of business. People will lose jobs, so it's unfair. So our objective for this project was to incorporate fairness into the optimal transport paradigm and to design a distributed algorithm for optimal transport that included the fairness constraint. So some background on what optimal transport is. In optimal transport, we have sources and targets. And by solving the optimal transport equation or optimization problem, you find a way to distribute the resources from the sources to the targets in the most efficient way. So each source and target node can be constrained by the supply and demand of the resources. So for example, back to the mines and factories, a mine may only be able to obtain a certain amount of resource out of the ground in a day, and a factory may only be able to take in a certain amount of resource in a day. So in the image that we show here, Q bar and P bar are upper bounds. So the sources can't produce more resource than what Q bar is, and the target can't take in more resource than what P bar is. And then they can also be bounded from below. For example, a factory would have to take in a certain amount of resource for it to remain profitable and remain open. And also, what this graph shows is the connection scheme between the sources and the targets. So it's not necessarily this connection scheme. We have every source connected to every target. That isn't necessarily true for every case. For example, the first source doesn't necessarily need to be connected to the second target, meaning that it can't transfer resources to that second target. So our problem formulation, and this is the problem formulation that is not with the distributed algorithm. So first we denote the set calligraphy X as the set of target nodes and calligraphy Y as the set of source nodes. And within those sets, we have the subsets X sub Y, which is the set of target nodes that are connected to source node Y, and Y sub X, which is the set of source nodes connected to target node X. And then we use uppercase pi to denote the transport plan, which is a set that calculates, or which is a set that holds the calculated transport plan between source X, target X and source Y at time t. So in our notation here, the subscripts X and Y is for X is the target, Y is the source, and then T is the time. And then we also consider the constraints for the target and source nodes. So P bar and P underline are the constraints for the target nodes, and Q underline and Q bar are the lower and upper bounds for the source nodes. So our transport plan between target X and source Y has to fit into both of those constraints. And then we also use the superscript T to denote the time that the transport plan is occurring at. So this is a discrete optimal transport formulation. So we want to maximize the utility over the transport plan. So here the functions dxy as the utility function for the destination, which is the same as the target, but because we're using superscript T for time, we're gonna refer to the targets as destination. Function S sub xy is the utility function for the source nodes, and cxy is the cost function for the source nodes. So there's some cost with transferring resources between X and Y. And then we sum, because we're in the discrete case, we sum rather than integrate over the sets. Y, our set of target nodes, or I'm sorry, our set of source nodes, set X, our set of target nodes, and time T. And again, we have the constraints that we mentioned in the previous slide, as well as the constraint that the transport plan between X and Y at time T must be greater than or equal to 0. So our fairness consideration. We choose a proportional fairness consideration because it allows an increase in utility without because we have to conserve the resources that are there. Obviously, we cannot create or and we want to take advantage of the resources that we do have. So that's why we need it. That's why we choose to use a proportional fairness function here. We also have to choose it to be concave and monotonically increasing. We have to do this because we want to do convex optimization. So we're gonna eventually, once we include this in the algorithm, we're gonna flip it. So we minimize the opposite of this function, and it'll become convex. So here's where we integrate our fairness consideration into our original optimal transport problem. So again, we have our utility functions for the destination and the sources, and then we add in our fairness consideration. And we can see that we subscript it with X, which means we're considering it on the target side. We felt that the target would be more inclined to want fairness. If we think back to the mines and factories example, a mine may not care where it transports its resources to, whereas a factory definitely cares about how much resource it's taking in. We also add in the weighting factor, omega, which can control the amount of fairness between target X and source Y. And we subscript it with X, meaning that we can change it with each source. So now we reformulate the problem in a distributed fashion. So first we make the transport plan between X and Y separable between the destination and the sources. So we superscript it with D and S respectively. And we can see here that they're equal. So pi sub xy superscript TD indicates the solution proposed by the destination node, and pi sub xy superscript ts is the proposed solution by the source nodes. And the reason that these are equal is because they have to be in agreement. We also need to define the sets as followed. So we defined the set uppercase pi sub d as the set of transport plans proposed by the destination, and uppercase pi sub s is the set of transport plans proposed by the source node. And then we also have the set f of d, which is the set of the plans by the destination, considering the constraints. And f of s is the set of the transport plans proposed by the sources, also considering their constraints. So here's our reformulation before we distribute the algorithm. So as we can see, instead of maximizing, we now minimize the opposite of the functions. And I should have mentioned before that we choose the utility functions dxy, sxy minus cxy to be concave functions initially. So now they are convex functions. And now we have to minimize over our destination sets, our source set, and the overall transport plan, uppercase pi. And we have to consider our new constraints such that the proposed transport plan by the destination and proposed transport plan by the source agree. So from that formulation, we can form the Lagrangian of the problem. So here, alpha xy superscript ts is the Lagrangian multiplier of pi xy ts, and then alpha xy td is the Lagrangian multiplier of our other variable pi xy td. So the reason we want to do this is because now we have our constraints considered in our equation, and that's captured by the later elements of the equation. So pi td xy minus pi xy squared, and pi xy minus pi xy to the ts squared. And then from a Lagrangian, we can apply alternating direction method of multipliers, or ADMOM. And from this, we obtain 5 equations. We obtain an equation for the proposed transport plan by the destination, an equation for the proposed transport plan by the source. We average those two to get the overall transport plan. And then we get an equation for alpha xy ts and alpha xy td. And now we can take the 2 equations for alpha xy ts and alpha xy td and combine them into one equation for alpha xy at time t. And that's why we have only 4 equations to the right here. And now we can rewrite those 4 equations into a much nicer algorithm that we see here. So while our destination and source transport plan is not converged, we want to keep on iterating through those 4 equations until we have convergence. And we can guarantee the convergence of this algorithm because we use ADMOM and we choose our functions correctly to be convex and monotonically increasing. So each node updates its strategy only based on the decision of the node that it's connected to. So that is captured by the first and second steps. So the destination considers the source that it's connected to and calculates the transport plan. The source considers the destination that it's connected to and calculates the transport plan. And then we consider the fairness in the target side of the equation, as I mentioned before. But then this fairness consideration is also considered by the source because of step 3. Step 3 is where we find a consensus between the destination and the source by taking the average of the two. So the overall transport plan will have the fairness consideration in it. So in order to verify that our distributed algorithm works and converge to the correct utility, we did case studies. So the first case study is with 5 source nodes and 2 target nodes with the constraints shown in the graph. Those are the upper bound constraints. We consider all lower bounds to be 0. So as we can see from and then we graph social utility, which is the aggregation of the total utility of the transport plan. So that would be the aggregation of the destination utility and source utility. So we also calculate this without the distributed algorithm to make sure that it's correct. And that is shown by the dotted line, so using a central planner rather than a distributed algorithm. And we can see that when we consider fairness, our algorithm converges to the centralized solution with fairness consideration. When we are not considering fairness, the distributed algorithm also converges to the solution proposed by the central planner. And then the distance residual makes it a bit easier to see how quickly it can converge to the proposed solution by the central planner. So for our second case study, we did an online version, meaning that the algorithm will update mid-calculation. So after we changed the network structure after 250 iterations. So we start with the network structure on the left with 3 sources and 2 targets, with the first source connected to the first target, the second source connected to both targets, and the last source connected to 1 target. So that's a good example of how the connection scheme can differ. So after 250 iterations, we change both our constraints and our connection and how many sources and targets we have. And again, after another 250 iterations at 500, we change it again. And we want to see if, even if we update mid-calculation, all our parameters, if the algorithm will still converge to the centralized optimal solution. And from these graphs, we can see that it does. So our social utility converges for the first 250 iterations, again, after between 250 and 500 when we propose a new problem. And again, after 500 iterations when we propose yet another problem. And then the residual here shows how quickly the algorithm can converge to the centralized optimal solution. And then we did a brief study on the effects of omega. So that was our weighting factor that we included in our fairness consideration. So as we increase omega, we can see that we increase overall social utility, which makes sense because as you increase omega, you increase the utility of the destination and thus the overall utility of the agreed upon transport plan. So in conclusion, we were able to establish a dynamic optimal transport framework that explicitly considers the fairness for resource allocation. We were able to distribute the algorithm using ADMOM. And the reason we wanted to do a distributed algorithm is because it is easier to scale. A centralized planner at scale can be difficult to work with, as can be computationally expensive. And then we also saw that our algorithm converges usually within 50 iterations in our investigated scenarios. And then, yeah, the large scale of the networks, or the distributed nature of the algorithm makes it applicable to large scale networks. It's much easier to scale up from smaller problems. And we did do a case study with 20 source nodes and 20 destination nodes. And again, the algorithm did converge to the optimal solution. And then our future work is to design a similar distributed algorithm that is resilient to nodes that might be hacked and thus deceiving or attempting to deceive the transport plan. So thank you for listening to my presentation. If you have any questions, feel free to reach out. My email is on the paper. Thank you.